Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's webinar, Fixing the Foundation First, Continuous Confidence in Robotic Software Infrastructure, brought to you by Circuit Cellar and sponsored by Solid Sands. I'm your host, Curtis Franklin, Editor-in-Chief of Circuit Cellar, and before we begin, I'd like to go over just a couple of quick details. Today's webinar is interactive. You'll be invited to take 2 polls during the presentation, and there will be a Q&A session following the presentation. To participate in both polls and the Q&A, please use the chat feature that you can see to the right of the display window. For the polls, there will be numbers that correspond to responses. Just type the number that best fits your answer and hit enter. For the Q&A session, you can enter your question into the chat window at any time during the webinar. I encourage you to not wait until the end. Go ahead and ask your question as it occurs to you. We'll see it and we'll answer it during the Q&A. If you ask a question that we can't get to during the webinar for time or other reasons, you'll receive a personal response to your question via email within 48 hours of the webinar's conclusion. With that, let's begin our presentation. Our speaker today is Sjoerd van der Zwaan, Chief Product Officer at Solid Sands. Sjoerd has spent more than 3 decades working at the cutting edge of robotics, autonomous systems, and safety-critical software. Today, he leads Solid Sands' strategy for compiler validation and library qualification, helping organizations navigate the complex landscape of software infrastructure ecosystems and gain absolute confidence in the tools building their software. Because fixing the foundation is a necessity when moving past the prototype stage and scaling into production, we have today's webinar to tell you how it's done. And with that, Sjoerd, over to you.
Thank you, Curtis, and welcome everybody. Good day, and welcome from a tropical hot Netherlands, where we are in 34 degrees Celsius or 95 degrees Fahrenheit. So it's steamingly hot here. My name is Sjoerd van der Zwaan, and I'm at Solid Sands. We provide the world's most rigorous test suites for compiler and standard library validation. We are based in Amsterdam, where the houses are built on wooden pillars that go through the layers of peat to find the solid foundation. You can see that image on the bottom right of this slide. And just like the pillars of those houses, our test suites ensure safety-critical software is built on a solid foundation. So today in this webinar, we will address the robotics trends. We are entering a new era of robotics. Machines are no longer isolated behind fences in factories. They now start walking besides us, actually. So they work with us, they adapt to us, and increasingly make decisions on their own. Today I want to talk about something we almost never discuss. Not the robot itself, not the AI, not even the application software. I want to talk about the invisible machine underneath all of it, the machine that builds the machine, and that are the tool chains that transform our software into executables. Because in modern robotics, trust does not stop at the source code. It must extend all the way down to the software tool chain itself. So let me go to the next slide. Here we go. So when a robot, a humanoid in this case, takes a step, thousands of computations happen in real time. Sensors interpret the environment, control loops stabilize balance, low-level software continuously corrects motion. And unlike traditional software systems, this is not confined to a screen or a log file. If something goes wrong here, the result is physical. Modern robotic systems make this even more significant. So today we are building new generation of machines, humanoid robots, but also cobots, or autonomous systems that continuously perceive, reason, and adapt to our environment. They are no longer executing fixed sequences, but instead they are operating in a dynamic, real-world context. And at the same time, they adapt intelligently, and high-level intent still ultimately depends on deterministic execution on the need. And that's what we are going to focus on in today's webinar. The challenge is not making the robots intelligent, it's also ensuring they interact safely within the physical world. So when we look at the modern robotics architecture, we can simplify them into three layers. We have the sense layer, the think layer, and the act. So the sense layer processes sensor data. It contains the vision systems and the software and hardware platforms behind that. LiDAR sensors, force sensors, environmental perception. That then plugs into the think layer, where the AI is at work. In the think layer, we solve navigation, we solve decision making, trajectory generation. But then ultimately, the act layer determines what physically happens. So that means how fast a motor reacts, how stable balancing remains, whether emergency braking activates in time. And that act layer is usually implemented in low-level C and C++ software because of its low latencies, high performance, and determinism. And this is an important point. AI may decide where the robot should move, but lower-level software determines how it moves, and whether it remains safe while doing so. And that is the lower level software is the software eventually running on the controllers that move the joints of your robot. So this is where things become interesting, because most engineering discussions focus on the application correctness, which you can see on the left side, where we have our software programmers and our software, our source code. It focuses on AI validation, it focuses on safety logic, but underneath of all that sits another critical layer, and that's the orange layer, or the development platform that we see in this picture. It is the compilers, it's the libraries, the linkers, the runtimes. These systems translate software intent into machine behavior. And first of all, the compiler takes the code that the software engineers write as input and translate it into executable code, the instruction set or assembly code that the hardware understands. So that's different from the source code. And this is much more than a one-on-one translation. The code that the software engineers write is an abstraction. So the generated code is much more complex. And what the generated code looks like is also completely dependent on the hardware architecture that is used in your system. So executable code for chip A might look completely different than executable code for chip B, even if the functionality behind it of the code is identical. But that's only the tip of the iceberg. Under the hood, compilers put a lot of effort in optimizing the code that the software engineer wrote. The goal here is to rewrite the software in such a way that it behaves exactly the same, but performs significantly faster. And this is, of course, a great advantage for developers, because they don't have to optimize their code themselves and consequently make it more complicated. Instead, they can keep their code as simple as possible and rely on the compiler to optimize it. Then after compilation, the libraries come into scope. The library is a collection of reusable software functions that developers can simply take off the shelf instead of having to develop it themselves. So libraries often provide fundamental functionality that any software project may need. Think of mathematical functions or reusable algorithms to sort data, etc. So yet again, this is a great advantage for the developer, because they do not have to reinvent that wheel and can instead focus on developing their latest and greatest software features. So together, the compiler and the library take away a lot of work from the software engineers, allowing them to focus on better and faster software development. Focus on your own application. But note that this is nothing new. Since the start of computing, compilers and libraries have always been used to develop software. And in other words, compilers and libraries truly are at the heart of the toolchain for bringing code into action. And as such, they play an essential role in robotic software. But every robotic action eventually originates from machine instructions generated by a compiler, which means that every robotic movement ultimately depends on software that most organizations simply assume to be correct. And that assumption is one of the least examined risks in modern robotics. And that's what we will focus on further in the rest of the slides of this webinar. But before we go there, we would like to launch a poll.
Very good. Thank you, Sjoerd. And as a reminder, it is now time for our first poll. You will see it appearing on the left side of your screen. And the question is, what best describes your production tool chain? Your options are: one, you use a commercial or proprietary tool chain. Option two, use an open source tool chain. Option three, a mixed tool chain of commercial and open source. Or option four, we're not yet in production. So please take a moment and answer 1, 2, 3, or 4 to participate in our poll. And Sjoerd, while our viewers are doing this, let me ask you, in your experience, do most companies use a hybrid system, or do companies tend to specialize either in a commercial tool chain or open source?
Yeah, basically both options are valid. We see both options at work and also hybrid systems at work in practice. And both options come with advantages. Open source, of course, gives you the most freedom. Commercial tool chains, a lot of pre-qualification work is taken out of hand, but still validation work needs to happen.
Very good. Well, we'll give it just a few more seconds before we stop this poll. And as a reminder to our viewers, this is not the end of their opportunity to participate in this webinar. We will have a second poll coming up a bit later in the presentation. And then, of course, there is our Q&A session coming up after Sjoerd's presentation. And we encourage you to go ahead and ask your questions as they occur to you. Just enter those into the chat window as well. Well, I'm going to stop our poll now, and we see that about half of our viewers here use a hybrid system with 25% each on commercial and open source. Interesting approaches, and I think we're going to have an interesting remainder of our presentation about tool chains from Sjoerd. And with that, Sjoerd, back to you to continue our presentation.
Thank you, Kurt. Indeed, interesting outcome of the poll, being it open source or proprietary compilers or libraries. That is something that we see as well with our customers. What I want to do next is dive a little bit deeper into what we call the silent risks. So where can things go wrong with your compiler or your libraries, independent of if they are open source or proprietary? So let's go there into toolchain defects. And these toolchain defects are particularly dangerous because they are silent. So a compiler bug does not announce itself. The build still succeeds and the executable still runs. But the generated machine behavior may no longer match developer intent. And unlike application bugs, compiler defects are systematic. So if a compiler miscompiles one safety function, It may miscompile every instance of that pattern across the entire code base. And I often compare this to a defective mold in manufacturing. So every product coming out of that mold may look correct, but will contain the same hidden flaw. So basically, what could go wrong? So consider the following failure: a compiler optimization that silently drops a safety critical check to improve performance. There are things that can happen. Or a library mismatch that causes subtle but catastrophic sensor data rounding errors, where exactly in an edge case on a flipping point could lead to dangerous situations as well. Incorrect instructions create memory corruption that is impossible to reproduce. So these are very latent issues, very hard issues to discover, and you want to avoid them. And we have seen real-world cases of such failures, and these aren't just theoretical risks. Over the years, we have seen numerous compiler library issues related to this, and without proactive measures, they can lead to failures. And that's why the safety standards also require qualification of compilers and libraries. Because basically, in the end, if you qualified your source code on the safety standards, and you can checkbox that on the left side, you qualified your hardware, you have redundant hardware in place. But now, what if the compiler introduces an optimization error? Or what if the library has an inaccurate library function that still would render your system into an unsafe system? And that's what you want to avoid. Then taking that knowledge to the robotics, there we see that robotic systems amplify these risks because robotic software combines real-time behavior, concurrency, hardware dependencies, has complex middleware, heterogeneous processor architectures, and also strict safety timing constraints. And at the same time, robotic platforms evolve continuously. There are updates, new middleware versions, new hardware targets, new AI frameworks, security patches, operating system updates. So unlike traditional embedded systems, modern robotic environments are constantly moving. And that is why you have to develop the confidence in your tool chain. So, but how do you do that? How do you prevent these kind of errors? Well, that's where a compiler and library validation comes into play. When you are using a compiler or a library, the safety standards require you to have confidence in the correct operation of the compiler. And they also require you to verify that the library meets the requirements that you rely upon. And how to do that is by performing qualification testing. By testing the compiler against the specification of the programming language, you verify that it correctly translates the programming language to machine code. And likewise, by performing requirements-based testing, you verify that the library correctly implements the requirements you rely upon. So in this graphic that's now on the slide, we illustrate this compiler and library qualification process. And it starts, of course, with step 1. And that is identifying the configuration of the compiler and the version of the library that you want to be qualified. Because only if you perform the testing using the exact configurations that you use to build your code, you develop the confidence that the compiler and library are considered qualified. So then step 2 is actually performing the qualification testing, generating the evidence, testing in and out the compiler and libraries, using test cases that verify each and every detail in your use case. And that way you ensure that they do what you expect them to do. Then step 3 is reporting on the evidence of your testing efforts. So then you are documenting how you have been testing the compiler and the library, how that meets the requirements for the compiler and the library qualification. And that way you provide the evidence that you have done everything in your power to make sure that you use the compiler and the library in a safe way. And be aware that here the goal is not to prove that the compiler or the library are free of any errors, because in practice, no compiler or library is perfect. Instead, the goal here is to be aware of the imperfections of the compiler and the library in such a way that you can do something about it and make sure that it does not impact the safety of your software. And then as a result, you will have a safety manual that describes how the compiler and library shall be used to ensure your software, your application runs safe while using that toolchain. And of course, all this effort and all this test effort, documentation and evidence then goes into your safety plan. And that is where you can offer a final step 4, the certification step. You will not certify the compiler or the library by itself, but it will end up on the stack of documents of your software that is being certified in the end. And only with a qualified compiler and library, you have a compliant development process that is ready to be safety certified. So historically, safety systems solved qualification by freezing the environment, because all of this is a lot of work. It's also a lot of documentation work. So historically, you would freeze the compiler, you would freeze the libraries, freeze your operating system, qualify once, go through all this work, and then change nothing. But that approach today no longer works. Organizations cannot simply stop updating software. Security updates are mandatory. Middleware evolves continuously, maybe even without awareness. Hardware platforms change over time, over product life cycles. And AI ecosystems move rapidly. So security updates alone make frozen toolchains already impractical. So now we face a fundamental contradiction. So if we do not update, systems become insecure and unsupported. But if we do update, previous qualification assumptions and all the effort that we went through generating that may no longer hold. And that creates a major engineering problem. Traditional qualification approaches were designed for systems that remain static, but modern robotic systems are continuously evolving. So that is where the tool chains enter also the compliance scope. So until recently, many of these discussions remained mostly engineering concerns, but now regulators are making them unavoidable. Within the EU, we have the EU AI Act, we have the EU Cyber Resilience Act, the new EU Machinery Regulation, and they are increasingly recognizing software and tool chains as explicit elements of safety and compliance. So particularly for robotic systems that use AI in safety-related functionality, the expectations of these regulations is shifting towards demonstrable evidence, not assumptions, but real evidence. So evidence that the software infrastructure remains trustworthy, controlled and verifiable over time, also post-production launch, and also including over-the-air updates during the complete product lifecycle. So that is altogether, in summary, I explained the silent risk with tool chains. I explained why that is amplified in robotic systems, which are complex, heterogeneous systems. And then there's also the update paradox. So systems can no longer be held as a freeze, qualify once and then freeze system. We need to cope with continuously evolving systems. And that is also where regulations are heading towards. So that is a lot of challenge. And before we go into a possible roadmap to tackle those challenges, we would first like to introduce a second poll here.
Thank you very much, Sjoerd. And it is indeed time for us to ask our second poll question. And that is, which of these statements best matches your qualification strategy? The possible responses are: number one, qualification isn't a current requirement. Number two, we qualify only when required by a project. Option three, we perform qualification for major releases. And option four, we continuously qualify our tool chain for internal purposes. Now, as before, please respond with one of these numbers typed into the chat window, which appears just to the right of our presentation window. And Sjoerd, I will ask you again, from what you have seen, is this something where the majority of the companies that you have dealt with choose one of these? I mean, is qualification something that companies just do as a matter of course, or is it sufficiently rigorous that they save it for when it's absolutely required?
That's a very relevant question, Kurt. So what's happening here is that first of all, there's regulated industries. It is a necessity. There you have to do the qualification and prove the evidence. But more and more, what we see is from safety integrity. And before going from prototype to rollout, you want to just make sure that you fix the foundations, because having to fix something later on when you are in production, when you are deployed, is way much more expensive. So the earlier you gain confidence in your toolchain, the better it is. And the best way to gain confidence is by validating. And the validation evidence is already 80% of your qualification evidence.
Very good. And we see, as with our first poll, we've got a variety of responses, with the majority saying that they do qualification, but only for their major releases. Well, that's going to come to the end of this particular poll, but it's not the end of your chance to participate in the webinar. We've got our Q&A coming up at the end of Sjoerd's presentation. We're looking forward to your questions and having a chance to talk about them with Sjoerd. So please go ahead, as they occur to you, enter those questions into the chat. We're looking forward to getting them answered. Well, Sjoerd, that's two polls down. We're going through the presentation. I can hardly wait to see how it ends. I'll turn it back over to you to complete the presentation.
Thank you, Kurt. So again, many challenges. So what we see is that in reality, the shift to continuous qualification becomes real. Qualification itself must evolve. Instead of treating qualification as a one-time certification event, we need to treat it as a continuous engineering activity. This is the idea behind what we call continuous qualification. And every relevant toolchain change becomes measurable. It becomes verifiable. It becomes traceable. And confidence is continuously maintained rather than assumed indefinitely. That is the shift to continuous qualification. And that is a strategy that you could adopt for when developing your systems and when you are facing these types of challenges. So what does that look like in practice, continuous qualification? Imagine a compiler update enters your development pipeline or your development system, or a compiler configuration change is activated. For example, an optimization flag is changed, or your application integrates a new component of a library that pulls in new library functions that up to so far have not been qualified. So instead of relying on assumptions, automated verification processes need to be triggered there. So compiler test suites then execute, library verification tests then runs, regression analysis compares results of your pre-established result that you already had on your safety documentation. You compare the current regression testing on that. Deviations are then identified, and with that, evidence can then be updated, or it can be flagged, hey, something manual now is necessary because you are stepping outside of your safety envelope that you had pre-established. So with such an approach, qualification then evolves alongside the software and the build system itself. So not after deployment, not once every few years, but really continuously for any compiler or library, being it proprietary or open source. You want to check that your build system, as it evolves, still matches your application code and your system, and that your pre-established assumptions still hold true or are being updated. That's how continuous qualification looks in practice. And that is a strategic roadmap if you roll that out, because it's not only about compliance, it's also about engineering scalability. Continuous qualification enables organizations to adopt updates faster, maintain safety evidence continuously, reduce operational risks, and avoid large certification bottlenecks. So in other words, safety and agility no longer need to conflict with each other. And that is also where we come into play. At SolidSense, this is exactly the challenge we focus on. So we are helping organizations continuously to verify their compilers, their libraries, and their software tool chains that they use in safety critical environments. And there are many examples of that. There's the medical industry, automotive, robotics industry, avionics, space, transport, etc. So what we have to offer is a ready-to-go test suite and a powerful test platform to perform the qualification of compilers and libraries. We deliver that to our customers in source code. They can integrate that into their development pipelines. So our product SuperTest is specialized in compiler qualification, while our product SuperGuard is specialized in library qualification. And the foundations of these products is our large test suite for C and C++ compilers and libraries that we have been developing over the past 40 years. So on top of these suites, we also offer our test platform, which provides the test drivers to automate the testing. And it also provides report generators to automatically generate the evidence that is required for safety documentation. Beyond the technology, we also provide the specific methodology and expertise needed for efficient toolchain qualification under safety requirements. So those are consultancy services that we also offer with licensed safety experts. And with that, it's very straightforward to qualify any compiler or library, open source or proprietary. It's straightforward. And then with SuperTest and SuperGuard, compiler and library qualification is actually only a matter of days or weeks. So the goal is not merely detecting defects. The goal is maintaining confidence that the software foundation that you use remains inside the qualified safety envelope as systems evolve. That's where we can help. Then wrapping up towards the end of this seminar. So I want to end also where I started. So when a robot takes a step, the control loops stabilize balance, low-level software continuously corrects motion, and there's a lot of attention going on worldwide to focus on the intelligence, the AI, the autonomy, the adaptation of these systems in a real physical world. But every autonomous decision eventually becomes machine code. And machine code becomes physical behavior. And the future of robotics, therefore, depends not only on intelligent machines, it depends on trusted software foundations as well. Because before we can trust a robot, we must trust the machines that built the machine. And those are the software tool chains. And that brings me to the end of this webinar. We are entering the Q&A session. But before we go there, of course, if the topics that are presented to you today resonate, please feel free to contact us. You can contact us through the email address here or through our website. But also, I've included here a QR code, which will bring you to our white paper that, together with our partner Buxing, we have written, and that's available on our website. So with Bugsang, we are building the framework for continuous qualification from the building blocks that both companies already have in place. We have compiler and standard library test suites. Bugsang has the building blocks to static analysis, perform static analysis on your source code, for example. They also have the building blocks to figure out automatically which part of the libraries is your application using. Now, what we are proposing to the market today is to connect all those products into a continuous qualification framework. And that's what we do as joint design partners. We are investing in developing such a platform, and we are also inviting launch customers to join our program there. And with that, I come to an end. And we still have time for questions. So let me look up in the chat, and I think we will go through them.
Sjoerd, as a reminder to all of our viewers, we do still have time for them to get questions in. We urge them to do so. In preparation for this, we actually had a couple of questions come in early as people had gotten their email responses for the webinar. And the first one is this: what are the biggest risks when moving from a robotics prototype to production?
That's a very good question. Moving from prototype to production, the main risks are safety regressions, update-related failure, and recertification bottlenecks. Continuous qualification then reduces these risks by continuously validating changes and maintaining up-to-date safety evidence.
A good, solid set of risks that need to be addressed, obviously, with the tool chain and the tools that you have available to you. Well, one of the things that you talked about in your presentation was confidence. And one of the questions is, can I trust the confidence claims of a compiler or tool chain without qualifying it myself? And I think the root of that question is, how deeply do I have to go through qualification in order to really have confidence in my tool chain and obviously in the product that results?
Correct. And this also brings us back to our earlier poll when we ask what types of tool chains do you use? So there are many pre-qualified compilers available in the market. They come with pre-qualification evidence. And of course, you can trust that. It comes with a safety manual. But you cannot entirely trust that. So vendor confidence claims help, but qualification of the compiler as you use it in your environment and with your application, that is what provides the objective evidence that a toolchain can be trusted. So that means either you stick 100% to the safety manual, then you also have to provide the evidence that you do that. So your type of activity changes a bit, or you requalify yourself, also the pre-qualified compiler, and show that your use case is safe using the compiler in the way you are configuring it.
I have a couple of follow-ups. One is, does qualification and confidence change if you go from a commercial proprietary tool chain to one that's open source? In other words, if you're using open source, do you then have to get into third party, fourth party, fifth party, sixth party risk, or do you treat both of them the same?
We treat both of them the same, and they should be treated the same. So any compiler or standard library should comply with the specification that comes out of the ISO standards for C++ versions. So it does not matter if it is a proprietary compiler or an open source compiler, as long as it complies to the specification, then On your application source code level, you can trust the compiler to correctly deal with the patterns that you program with in your application.
Very good. Now, we've looked at both internal and external um, instigators for compliance. The Cyber Resiliency Act, the Cyber Resilience Act, how does that affect toolchain qualifications, and does it add any urgency to the compliance and qualification questions?
Yeah, so to start with, the Cyber Resilience Act is an EU market act, and it increases. It does not dictate you shall qualify your toolchain directly, but it increases the need to manage software updates throughout the product lifecycle. And from that, indirectly, that means that for safety critical systems, organizations must ensure that the updates maintain both cyber secure and safety compliant. And then continuous qualification again helps assess updates and the impact thereof efficiently, and also maintain the evidence needed for ongoing compliance. Because it's not only doing it, but also showing the evidence.
Very good. Now, that is bringing us near the end of our webinar today. And Sjoerd, before we go, just wanted to give you a chance. If someone is leaving here, is there one key thing you'd like them to walk away with? One thing that you want them to keep in mind as they get on with the rest of their day?
Definitely. Our recommendation would be fix the foundation first and do it as early as possible. And then do that once, create a baseline, and then start looking for strategies to maintain that over updating and evolving systems.
Outstanding. Well, that concludes today's webinar, Fixing the Foundation First, Continuous Confidence in Robotics Software Infrastructure. I'd like to thank our speaker, Sjoerd van der Schoon, Chief Product Officer at Solid Sands, for joining us today. And our thanks to you, our listeners and viewers. Please keep your eyes open for future Circuit Cellar webinars, including our next webinar, Comprehensive Testing for C++ Multi-Threading Primitives, scheduled for July 8th at this same time. Today's presentation is copyright 2026 by Circuit Cellar. All presentation materials are the property of the presenter and may not represent the views or opinions of Circuit Cellar or KCK Media. Thanks for joining us. Have a great day.